Hi, everyone. Welcome to this session of BTR 7. My name is Sahar Ghanipur Machiani. I'm an associate professor here at San Diego State University, and I'll be chairing this session. We are excited to have you join us today and look forward to a great lineup of presentations that we have. Each speaker will have 15 minutes for their talk, followed by a brief question and answer. Please feel free to type your questions in the chat or raise your hand at the end of each presentation. Let's get started. Our first presenter is Ian Brody, presenting their paper on a multi-source reconstruction of the 2024 Jasper Wildfire Complex. Ian is a master's student at the University of Alberta, specializing in transportation engineering. His research focuses on wildfire evacuations, exploring innovative ways to collect travel pattern data and improve evacuation planning for the future. Ian, please go ahead and share your presentation and start it.
Sounds great. Okay, can you guys hear me good?
Yes.
You can see my screen too?
Sure.
Okay, perfect. I will get started here then. Hello, everyone. My name is Ian Brody, and I am here presenting my research on a multi-source reconstruction of the 2024 Jasper Wildfire Complex. Now, this work was done with my co-authors, Dr. Stephen Wong, Max Natter, and Dr. Nordine Benichau. So without their help, this presentation would not be possible. So to get started, why are we doing this work? Well, wildfire events are becoming more intense and frequent. So with time, there's been a lot of events in the last few years, notably the 2016 Fort McMurray wildfire, the 2018 Camp wildfire, and the 2023 Maui wildfires. All of these were devastating in their own regards. And just last year, there's the 2024 Jasper Wildfire Complex, which is what this presentation is going to be about. And since then, in early 2025, there's been the 2025 Los Angeles wildfires, which had a large amount of losses between 76 and 131 million based on early estimates. So there's a really need to understand these events better and how we can plan and ensure that the future events that happen with this scenario are better equipped for life safety. So I'll give a little bit of background about Jasper. So these two maps here highlight where Jasper is. So the one on the left shows a bit of a larger picture. Jasper is a place here in Canada, in the province of Alberta, but very near the province of British Columbia, right near the Rocky Mountains. So the map on the left kind of shows that outer view. It has three major routes that run through it. So Highway 16 goes to the east and goes to the west, and Highway 93 goes to the south. So three routes in and out. However, those routes, if there's issues like there was last year, can get really damaging. So what happened was there was two initial ignitions, one on the east side of Highway 16 and one on the south side of Highway 93. So because there was those two fires, those routes were not available for people to evacuate, leaving one singular evacuation route on Highway 16 towards British Columbia, towards the west. So another bit of background about Jasper, its population is usually around 3,000 permanent residents. However, in the summer months, this falls to 20,000 with seasonal workers and tourists present in the area. Additionally, within Jasper town site on the map on the right, there's only 3 exits out of the town site towards the highways, and there's also a bunch of campgrounds and resorts in the nearby area, such as the ones shown on the map there. So we can do a brief timeline of what happened during this event. So it began on the evening of July 22nd at 8:28 p.m. There was an evacuation alert issued. At 9:59 p.m., that was upgraded to an evacuation order. And because of that, there was everyone was declared to leave the town, and all of these sort of evacuation procedures begun. So that was happened on the evening of July 22nd in the late hours of the day. On July 24th, 2 days after the evacuation had occurred, significant losses were reported in Jasper, and about 30% of the community was destroyed to fire. Now, after that, over this 24-day evacuation, the Highway 16, which is that major highway I mentioned, was slowly opened to commercial access beginning on August 1st, and eventually upgraded to evacuee traffic on August 4th, before all traffic was allowed on August 9th. So during this course of the wildfire, there's an incremental opening of Highway 16, And this finally accumulated when reentry for the community of Jasper began at 6:30 in the morning on August 16th. So that's kind of a bit of background of where it was, kind of what happened during this event, just for a bit of context for those who do not know. Now, for this multi-source reconstruction, we can think of how are we doing this? So we're using 3 different data sources, and our goal is to kind of piece them together and create a wide view of what really happened. So the first one that I'm going to talk about is a little bit more unique and novel. It's called network mobility data. So this is a privacy protected, de-aggregated and de-identified and aggregated source of mobile phone traces. It's provided by TELUS, which is a Canadian telecommunications company, and we get this through the TELUS Data for Good program, which provides researchers and other people the opportunity to look at this data for societal good. So these mobile phone traces, but how number of traces are there? Where do they get it from? So based on in Canada here, TELUS accounts for 50% of the population in Alberta and 42% in BC. So with these high amounts of population, majority just about in Alberta and close to the majority in BC, TELUS uses a series of proprietary factors to extrapolate these amounts to the entire population. So the amounts and information that we receive are the total amount of information for these areas based on this extrapolation. Now, you might be asking how a device is counted. So it's counted 4 ways. The first one is if it receives or sends a phone call or a text. The second is if it uses data. The third is if it connects to a new cell phone tower. And the fourth is if it's remaining dormant in the same area, it will continue to be counted in that initial location. So that's kind of what network mobility data is and how it can be counted. Now, to make this multi-source, we combined it with traffic counts. So traffic counts, pretty self-explanatory. I don't have to go in a lot of detail here. They count vehicles passing through a counter. And along Highway 16, just to the east and just to the west of Jasper, there are traffic counters present. And these record hourly details of lane volumes, and then we get them open source from the Alberta government. Now, the third one here is the social media posts. So we used social media posts from official government pages like Jasper National Park and Jasper Municipality. And we use these mainly to create an in-depth timeline. So that way we compare what we see happening with network mobility data and traffic counts to what we see happened with social media posts. And this creates a really in-depth and detailed timeline. And on the previous slide, you guys saw a summary of that timeline. So that's kind of where the social media comes into play. And that's how we connected them all together. Moving forward, I'll start to dive into some of the interesting thing, which is the results. So this one's called unique devices results. You might be asking unique devices. That, of course, comes from the network mobility data. So unique devices are the number of devices within a geographic boundary by hour. So that just includes a simple count of devices in an area. Now, we can look at these unique devices in, you guessed it, Jasper, which is where it was evacuated. And the figure here on the map shows the amount of unique devices within the Jasper municipal boundary over the course of the 24-day evacuation and a little bit before and a little bit after as well. So the green shows the 2023 device counts and the pink shows the 2024 device counts. Now, upon first glance, it's pretty obvious. You can see a really big evacuation jump. So it goes from close to 17,000 way down to almost closer to 0, just about 25,000. So there's a really big drop of device counts of 15,000 overnight on July 22nd. Furthermore, if you keep looking at that, as I mentioned, July 24th is when all people without self-contained breathing apparatus in the town site, so emergency personnel and all that, were evacuated due to fire encroaching. And you can see a drop there on July 24th. Afterwards, it's pretty stable, close to 0. There's a bit of oscillation, which would account for the highway running through Jasper. And then August 16th, you can kind of start to see a slow rise of people going through. So it increases for reentry, but as you can see here, in a town where structural loss occurred, device counts never matched the 2023 totals after reentry had occurred. So we can kind of get a little bit more information from this. So if we take that evacuation drop, kind of push it down and expand it a little bit more to see what changes, we get this evacuation curve. So now we started the evacuation curve at the hour nearest to the evacuation alert, and we counted the cumulative number of departures that occurred in the community. So as you can see here, it starts just after 8 p.m. and it runs all the way till 8 a.m. in the morning, but departures stabilized at 6 a.m. in the morning. So that means from the evacuation order at 10 p.m. to departure stabilization at 6 a.m., we have an evacuation time estimate of 8 hours. One thing I'd like to point out is that there are minor impacts after the evacuation alert was issued, the slight rise in departures. However, there are campgrounds, resorts outside of the Jasper municipal boundaries that people might be traveling to, so it's hard to declare if that's fully evacuation traffic or the impacts of other traffic. However, after the evacuation alert, we really see that evacuation order, we see that really big rise. Now, an interesting thing here, the final point I'll make, is that this curve, while it's slightly S-shaped, it's pretty stable. There's a very stable rise in device count. It doesn't curve like a lot of times we see S-shaped curves for evacuation. So there's around 2,000 device departures per hour. And additionally, there was also congestion reported during this period. So we have hypothesized that there's likely impacts of the transportation network that are causing this kind of change in device count evacuation and shifting from that S-shaped curve to a more stable based curve. Now, to kind of elaborate on this a little bit more and to try and make some more impacts for future evacuation studies, we fit mathematical functions to this curve. So they're listed on the side there: logistic, Rayleigh, Poisson, log normal, and log logistic. And these all come from previous studies. So it's hard to see really on the figure there because a lot of them are very close together, but the Poisson root mean square error was about 0.036, which is the lowest amount. Now, the logistic and Rayleigh RMSEs were 0.0348 and 0.0385. So pretty close in magnitude, not a lot of difference, which shows that they likely have good applicability in modeling evacuation curves. Log normal and log logistics were around 0.055. So pretty similar still, but slightly less of a good fit. We will say that no function captured the very unique stable departure rate that we found here. So that is a point that could be made, that potentially these evacuation curve functions may not be the most applicable to this specific type of evacuation. Moving from back, kind of if we go back to that main figure and we dive into reentry period here, we can look at that. I did not create a reentry curve. As you could see, there's these really big oscillations in count. So we really don't have a stable picture of how reentry occurred without jumping up, back and down with cumulative arrivals. However, TELUS allows us, through their program, to separate residents from non-residents. So in this figure, all devices are in green, Jasper residents are in purple, and Jasper non-residents are in gray. So when we look at that, we can kind of see that Jasper residents slowly crept up, and only 11 days after the evacuation occurred, or evacuation ended with reentry occurring, did we see that resident counts past 2,000. So there was a very long term for reentry to occur. So just in summary for this unique device section, we observed 15,000 device departures. We had an evacuation time estimate of 8 hours, and departure levels were pretty stable at 2,000 device departures per hour over the course of the evacuation. Poisson distribution best fit the data, but no large differences were really observed through the other functions. Reentry was highly oscillatory, so likely there's impacts of background traffic, support staff, those who are not staying in the community but are helping out, something like that was creating these oscillations. However, devices never matched the 2023 totals, and structural loss in the community likely was highly impactful here. So now I'll switch gears and kind of talk about another thing we can do. So origin destination pairs, pairs between Jasper and communities nearby. So in this case, Jasper Hinton, Jasper Fraser Fort George Electoral District H, which is kind of the county equivalent of the area to the right. So we can see these pairs between two sources, and that is network mobility data and traffic counts. So if there's traffic counters along Highway 16, and we can use network mobility data to count the number of devices that travel between these two areas. So there's a lot of work that we did in this kind of forte, but I'm only going to present one pair, which was the evacuation route, which is Jasper heading westbound. So that map kind of in the top corner shows the pair I'm talking about, that kind of green line away from Jasper, which people had to evacuate on. And this slide showcases specifically the network mobility data. So again, green is 2023, pink is 2024. And really obvious, we can see this really big peak in evacuation, close to 2,000 device trips, which matches kind of what we've seen before. And we see that evacuation really jumped, and then it's pretty stable. There's not a lot of travel even before Highway 16 is opened. And once Highway 16 is opened on August 1st, we see slight numbers, increases a little bit more when all traffic is opened. And then with reentry, there's traffic is similar, but it is still from below 2023 levels. So that's kind of what we see along the evacuation route with network mobility data. But what we can do is compare network mobility data to traffic counts along this evacuation route. So when we do this, we see this pretty similar, right? So network mobility data is in orange and traffic counts are in blue. And what we see is a really big jump for network mobility data, but we also see the same jump for traffic counts. So the valleys and the peaks in one are also shown in the other, which shows a degree of cohesion between the two of them. There are varying device counts per vehicle, which is why we see traffic counts as lower than the network mobility data counts. But this does point to the validity of both sources when investigating future evacuations, as they record the same events. We see the same amount of information between the two of them. And just as kind of another thing, I'll just quickly jump in here to the evacuation route itself. And if we zoom in on that evacuation period, we can see the number of vehicles passing through the counter was relatively stable around 800 vehicles per hour for the peak 5 hours of the evacuation, which matches what we saw in the device departure rate, but this is well below the capacity of the road. So in summary, network mobility data and traffic counts identified the same valleys and peaks, and a flow rate of 800 vehicles per hour was observed over 5 hours in the traffic counts. This is significantly less than the capacity of a single lane rural highway, but we also had reports of congestion along the evacuation route. So in turn, this kind of points to impacts to the maximum sustainable evacuation flow rate for wildfire evacuations, saying that there might need to be a significant reduction in the capacity of a highway during wildfires based on what we can see in this data. So lastly, key takeaways: transportation network likely limited the departure rate to 2,000 device departures per hour. A single lane rural highway was observed to carry only 800 vehicles per hour during the evacuation peak. Contraflow, shoulder lane use, and our transportation network changes are likely needed to lower ETEs from the 6 to 10 hour range here, and also seen in previous research. And the final peak is that reentry featured a slow, weeks-long arrival rate of residents with daily oscillations of non-residents. Here are my references, and then thank you to TELUS and the Data for Good program. And we have a similar paper that talks about network mobility data for the May 2023 wildfires. So I will leave that for people to take a look at.
Thank you. Is there any question? You could type it in the chat box or just raise your hand if you have any questions. And if not, thank you so much, Ian. Oh, there is one. Given the data is de-identified, would it be possible to look at evacuation over time based on rough location? Example, people closest to the fire leaving first.
That's a fair question. With TELUS, they do provide another option that instead of looking at municipality boundaries, you can look at postal code boundaries. However, Jasper has the same postal code for the entire thing, so we're not able to see differences really within the municipality. But an additional point is that due to the privacy restrictions that they give us, if it's under 30 device trips per hour, they just report it as 0 and we do not see any information because of privacy concerns. So the only issue is when you start to get smaller and smaller with some of these locations, you still need a sufficient population to have more than 30 device trips per hour just to make sure that we actually get data reported. But that is definitely a way we can look at for future studies and evacuations, especially if they do have more granular division on the postal code level. Or I guess zip codes, as some other people call it too.
Thank you so much, Anne. Okay, we are going to move on to our next presenter, Jelly Lee. So Jelly is going to present their work on a two-stage restoration approach for road networks after disruptive natural disasters. Jelly is a PhD candidate in transportation engineering at Florida State University. His research focuses on public transit, transportation investment under uncertainty, and the development of equitable and resilient transportation systems. Jelly, please go ahead and start your presentation.
Thank you for your introduction. Can you see my screen and listen my voice?
Yes,
all right,
all
thank
good.
you. All right. Okay, so today the topic of my presentation is the two-stage restoration approach for road networks after disruptive natural disasters. Let me briefly introduce my collaborators. I'm Jelly, a PhD candidate in Florida State University, and Daniel is a PhD student at Florida State University. Daniel works on machine learning, deep learning, and intelligent transportation systems. And this is my advisor, Dr. Qianwen Vivian Guo. And a brief introduction of our group, we do a lot of projects on public transit and emerging technologies, such as the vehicle occupancy estimation using Wi-Fi technology. We also do the digital twin and drone delivery. Florida, as a coastal state in the US, it has the highest risk for flooding, and Florida has experienced significant economic losses from floods. Here's an example of Hurricane Michael in 2018. The hurricane has led to more than 45 deaths and more than $25 billion in damage. And as you can see, the recovery is a long-term process. The recovery takes like more than 5 years. And we focus on the road network because the road network plays a very important role in ensuring the economic and social well-being of residents. And repair and reconstruction of road networks takes a lot of material and labor resources. When we look into the literature, when we search the keywords such as the resilience and the road network restoration, we find that recently there are more and more publications on this topic when we search the transportation related journal. So this is also a very important topic. And there are a lot of studies focusing on the post-disaster recovery. They work on the road, electricity, gas, water restoration. They have different objectives and they have different problem sizes. As for the road network recovery, basically there are two stages as you can see from this figure, figure 1. So the first stage I call it network connectivity, and the second stage is called the performance improvement. There are two distinct stages, and each stage has its different properties. For example, the stage 1 it requires to restore the basic connectivity between all nodes of the road network, and the stage 2 tries to enhance the traffic flow and reduce the total travel time. And stage 1 is typically the short-term response. It requires the rapid or minimal repairs to guarantee the minimum required performance. And stage 2 is typically a long-term process. It requires the comprehensive reconstruction. When we look into the literature, we find that most studies focus on the stage 2 restoration. They focus on the performance improvement, but they seem to ignore the basic connectivity, which is the stage 1. Stage 1 requires to recover the minimum required performance. So this is one research gap, and that's why we propose this two-stage restoration process. And let me briefly introduce the network classification. So a network is strongly connected if you can go from any node to other nodes, like in figure A. And the network may be connected but not strongly connected. So as you can see from this figure B, all nodes are actually connected if you do not consider the directions. But if you do consider the direction, here's an example. You cannot go from this point to that point. So this means the network is connected but not strongly connected. And the network is disconnected as shown in figure C. That means there exists some node that is not connected. You cannot go from one node to another or from another node to the first node. So this is the network classification. So why we propose the stage 1 and stage 2 restoration? Because we find that most studies assume that the network remains strongly connected as in figure A after the disruption, but it may not hold after very severe disasters. That means we need to re-establish the basic connectivity. We need to make a disconnected network to a strongly connected network. This is a critical first step. So let's discuss the stage 1 connectivity expansion. As I explained earlier, we want to make a disconnected graph to a strongly connected road network. So the question is to restore as few links as possible, such that the restored network is strongly connected. That means all nodes are reachable from one another, and we want to minimize the total cost. But there's a question. How do you formulate this problem? What's the mathematical formulation of strongly connected or reachable? How you use the mathematical formulation to express that any two nodes can reach each other? So you may consider a similar problem, solution check. That means if you are given a restoration plan, how do you check if the network after restoration is strongly connected or not? One potential solution is by enumeration. You can enumerate all potential candidate roads from any two nodes from origin R to destination S. And when you list all the potential routes, you want to verify to find if there are at least one route that is available. But the drawback is that there are too many solutions to enumerate, especially if you consider a large-scale problem. From one point to another point, there are so many roads. So another similar problem is actually the min cut problem. If you are not very familiar with this idea, I show you in a figure here. So basically, these problems ask you what is the fewest number of green tubes. You want to cut the fewest number of green tubes such that there's no water available from this hydrant to the bucket. So this is called the min cut problem, and you can find what is the minimum number of green tubes to be cut so you cannot go from this hydrant to the bucket. And this is borrowed from the graph theory, the computer science idea, and this problem is equivalent to the max flow problem. And that means you want to find at least one. If you consider the road network recovery problem, that means at least one cut should be repaired to make sure the network is strongly connected. That means if you see the hydrant as the origin, the bucket as the destination, if it's disconnected, you want to make sure at least one edge from this min cut set should be restored. And there are some efficient algorithms to solve this problem. And by this idea, we can formulate it as follows. So we want to minimize the restoration cost. The decision variable is whether a link is repaired, and as RS is the min cut set, we want to make sure at least one road link from this set should be repaired. And the solution is that for any disconnected nodes, you can generate those connectivity cuts, solve this problem, then verify. There are some technical issues I do not have time to discuss in details, but basically the min cut is not unique, and it may include links that are not damaged. So we need to modify this problem. For example, we assign capacity of 1 to damaged link and capacity infinity to undamaged link. And since this is necessary but not sufficient condition, we need to solve it by iteration. So here I show some results of numerical experiments. We generate some random networks and we randomly decide which links after disruption are damaged. And this is the restoration process. The last figure shows what is the restoration result of the road network. And as I mentioned, it's a necessary but not sufficient condition. So basically, we need to solve it by iteration. This is what the restoration looks like. And we also change the disaster severity. If the disaster is more severe, that means there are fewer road links to be available after the disruption. And what is the restoration looks like? Basically, it seems that no matter the disaster severity, the network after restoration looks similar. And we also change the road density if the road is more dense, as shown in the second row, and what is the network after disruption and what the restoration looks like. And we also change the network size. Basically, if the network is larger, there are more nodes and links, and what's the disruption, the network after disruption, and what the restoration looks like. In the future, we plan to apply the graph theory to make the algorithm more efficient because there are some strongly connected components in the network. That means some nodes are reachable from each other. Then we can group them together. And when we make the restoration, we can use the weighted strongly connectivity augmentation that will make the algorithm more efficient when you consider the large scale problem. And we want to argue that the network restoration is different from the network design problem. If you are familiar with network design, actually it's only one or several OD logistic network, or if you are given an existing road network and you want to expand it. But for the network restoration, the original network is actually existing, and which node should be which links should be recovered is a given set. So these two problems are different, just to clarify. And now let's briefly discuss stage 2. It's called performance improvement. Now you have a strongly connected network after the stage 1 restoration. And you want to, so basically this is a long-term recovery process. You have multiple periods. Each period has different days with different budgets. And you want to improve the network performance. And this is the standard problem formulation used in the literature. It's a bi-level optimization problem. The upper level is trying to minimize the total system travel time. The decision variable is which link to be restored in which period. And we need to solve the lower level problem. It's the traffic assignment problem. Solving the traffic assignment problem, you can get the total system travel time within the transportation network. But this problem is very challenging. Why is challenging? Because even if you simplify the problem, it's already very challenging. The first implication is that if you consider a one-time restoration, it's similar to a knapsack problem. That means you need to decide which links to repair, and each link has different values and costs. But it's actually more challenging because the marginal gain of restoring a link, actually it depends on which other links are also restored. And the second simplification is by scheduling. If exactly one link is repaired during each restoration period, then this is actually a scheduling process. And there are some studies discussing, they propose some algorithm to solve it, but this is still challenging when you look into the original problem. So why is this problem challenging, especially when you solve the large-scale problem? Because the marginal gain of restoring a link actually depends on which other links are also restored. So you need to solve multiple traffic assignment problems as subproblems. But solving the traffic assignment problem is already very challenging. Even if you use the most advanced method, it basically take, like, for example, the Chicago network, it basically take you 5 minutes to solve the problem. And you need to solve multiple traffic assignment problems as subproblems. So that's why this is not efficient, because even if you only solve one problem, it's gonna take some time. So we propose some heuristic algorithm, try to solve limited number of traffic assignment problems as subproblems. As I mentioned, this is a bi-level problem. The upper level is to decide which links to restore, but the information is from the lower level problem by the traffic assignment problem. The first heuristic is trying to estimate the value of repairing a link. For example, if the link is repaired first, it may have the larger gain of restoring the link. And if it's restored last, then you can get the lower bound. And by this lower bound and upper bound, you can estimate the value of repairing a link and repair those links with the highest value first. But again, this is just a heuristic. We cannot guarantee the optimality. The second heuristic is trying to update the values periodically, so the estimation of the marginal gain of restoring a link is more accurate, but you need to solve more traffic assignment problems as subproblems. The third heuristic is try to do the local optimality. You can do the gradient and local search in each period, and you need to solve more traffic assignment problem. Actually, it's a trade-off between how many traffic assignment problems you solve and the accuracy, how and what's the optimality gap of your restoration results. You decide which links to repair. So here's the brief numerical experiments. So we consider two sequential periods. Each period has 2,000 unit budget, and this is the network after restoration. Stage one, this is the network after stage one restoration, and in stage two, there are two periods. Each period's 11 undamaged links were repaired. And in the future, we hope to compare other heuristic methods like genetic algorithm to see if there are any improvements. But again, the challenge is to solve limited number of traffic assignment problems, and maybe there are some exact methods that can be proposed, but it's very challenging. So as a summary, we propose a two-stage restoration approach for road networks after disruptive natural disasters. We identify two identical stages. The first stage is connectivity expansion. We want to make sure the disconnected network to be connected first. And the stage two is called performance improvements. We want to minimize the total system travel time within the network. And basically, this is the framework, the algorithm proposed. We want to solve the large-scale problem with many nodes and road links. This is still ongoing. We plan to apply the methodology to real-world transportation networks and test its scalability and efficiency of post-disaster recovery. We explore different restoration goals and test different methods. And this is my presentation. Thank you.
Thank you, Jelly. Is there any question for Jelly? And I see, Vivian, you had a question that we missed. Sorry about that, but I see that Ian already replied to your question. That's great. Thank you. Okay, any question for Jelly? Okay, there is no question. If you think of any question later, oh, there is one coming.
Oh, I just saw the question.
Yes. Is this something you would solve in advance or reply to a specific network road closure scenario after the natural disaster?
That's a great question. This is something we need to solve after the natural disaster. So we have the original road network, and after the natural disaster, we will know which links are damaged. So once we have which links are damaged, we need to decide the restoration plan. As I mentioned, this is a long-term process. It has two stages. In the first stage, you need to decide some links, which links to repair to guarantee the basic connectivity. Because you only have limited budget and the time duration is short, and the second stage is to enhance the connectivity. So basically, when the network after the disruptive event and some road links are damaged, then you decide which links to restore. So this is basically a framework, algorithm to tell you what to do.
Thank you. Okay, looks like there is no more questions. Thank you so much, Jelly. And we are going to move on to our next speaker, Ji-Sung Lim. Their paper is titled Navigating Uncertainty in Curve-Space Development Planning via Stochastic Optimization. Ji-Sung is a PhD candidate in civil engineering at University of Michigan. He is also a 2025 Rackham predoctoral fellow and a 2024 FHWA Eisenhower graduate fellow. Ji-Sung's research focuses on transportation systems, including network modeling and optimization, game theoretic, policy design, and intelligent infrastructure planning. Thank you, Ji-Sung. You could begin your presentation now.
Hey, hello. Thank you for the kind introduction. My name is Ji-Sung from the University of Michigan. I'm delighted to discuss about my research titled Navigating Uncertainty in Curve-Space Development Planning via Stochastic Optimization. So let's begin. Transportation infrastructure has long been a critical component in human's life. It has served as a backbone of numerous systems and services that helps our daily well-being. So historically, transportation infrastructure first accommodated mass movements of people through arterial infrastructures. Then, about a century ago, with the introduction of a personal or private vehicles, people started to use transportation to address their individual travel needs. Today, with the advent of new technologies such as connectivity, automation, electrification, and the shared mobility, we are seeing the new paradigm shift in transportation infrastructure, namely the next generation mobility systems. Among different components in transportation infrastructure, CurbSpace has emerged as a critical location that can accommodate different evolving transportation modalities. It is serving as a hub or access points of various urban operations, and its value comes from by providing the best proximity to different urban activities. Furthermore, it is shown in the literature that the dynamic operation of these spaces can be helpful in boosting the utility of the people using the curb and increase the adoption rate by the people. So my research question is as follows. So I want to impose a strategic planning on the curb-based infrastructure development. In particular, I want to seek a balance between the spaces that will require permanent installations, for example, EV charging stations or micromobility docks, versus spaces that can be allowed for the dynamic services such as street parking, pick-up drop-off, or freight loading and unloading. Furthermore, when we develop this infrastructure development planning, I want to seek where and when to invest for the infrastructure upgrades, particularly for the ones that require permanent upgrades. However, this is not an easy task, and that is mainly due to the uncertainty in the pace of technological advancements in curb-based modalities. For example, the bottom two pictures show how people decades ago envisioned the mobility system in year 2000 would be. Obviously, some are true today, some are not even realized by today. But this is how the uncertainty can be unfold differently as the time frame reaches. So this phenomenon can be also applied to a curb space where different pace of technological advancements will shape the user demand and composition differently in the future time frame. That will impact the curb space utilization, and it will also impact the investment payoffs that we have to pay beforehand before the time comes. To overcome this challenge, I propose a two-stage stochastic optimization model that helps us to evaluate the long-term value of investments in curb space infrastructure under the uncertain future demand levels and compositions. This problem is comprised of two parts, so I'll dissect into one by one. The first stage problem develops and suggests an improvement development planning across the time horizon. It consists of three constraint sets. First is about the development decisions denoted with this flow variables x. This x flow variable denotes what status is each curb space is in to accommodate which type of modalities. You can see the structure is as that of the network flow model, where each decision variable becomes a flow path or flow variable between the two nodes. The second set of constraints calculates the development cost based on these x variables decisions. This data is comprised of the variable cost, fixed cost, and the one-time electrification cost. Finally, we want to check whether these developments are under the budget allowance. In particular, we want to check whether each budget used at each time is under BT, and the entire budget allotted for the entire time horizon is under the constraint B. Overall, the stochastic optimization model tries to minimize the budget used. Plus, it also maximizes the expected utility of the curb space operation as the demand uncertainty denoted in D tilde is realized and is unfolded in the future time frame. Now let's go to the second stage, or the recourse problem. In the recourse problem, first, the supply of the spaces for each modality at each time is denoted by the summation of the x decision variables, which denotes, again, the decision of development planning. The uncertain demand D tilde is here also, which takes a distributional form in the original problem setup. And now you can see in the problem, this setup is very similar to a transportation or assignment problem, which has well-known polynomial time algorithm to solve. Another feature in this recourse problem is that when we distribute the supply of spaces S across the uncertain demand D tilde, we can see the summations is defined over set P prime. Set P includes the set of curb space zones, and P prime includes one additional dummy zone, which will capture either user attrition or the loss of demand due to insufficient number of spaces. With the existence of this dummy node, we can argue that this problem has complete recourse, which helps us to reach to the optimal solution more easily. However, this recourse property is oneself cannot help us to overcome all the scalability or the tractability issue. As such, I impose a series of solution methodology to enhance the scalability of the problem. First, I apply a sample average approximation or SAA method, which allows me to replace the uncertainty set regarding the uncertain demand levels with an empirically approximated set through a Monte Carlo sampling. This SAA method has two components. First, through an approximation problem, I use a coarse approximation using the coarse Monte Carlo samples to quickly devise and propose new development planning schemes. Then, in the second stage recourse problem, I shape this recourse problem using the policy vector obtained from the approximation problem. Then I'm going to apply more refined Monte Carlo sampling to the uncertainty set, which will allow me to have more accurate approximation of this set. Then I'm going to assess the planning quality proposed by the approximation problem, and this process will go iteratively. On top of this, I'm going to also apply a path-based reformulation to the original model. Recall our development decisions are made by a network flow model. Then each of the decisions indicated by an arc here become decision variables in our problem setup. Now you can see as the time dimension or the number of modality grows, the number of these decision variables will grow exponentially. As such, I propose an alternative modeling where I express the sequence of development plans as a path, and each path will now be a decision variable in my first stage problem. Where this path-based reformulation itself cannot alleviate the scalability problem entirely, it becomes a prime foundation of devising this column generation solution methodology. In column generation, we do not consider all the path variables, but instead we introduce them one by one iteratively until we note and identify all the highly priced decision paths. So with these three methodologies integrated, the solution algorithm is as follows. First, we're going to generate a coarse approximation of our uncertainty set regarding the future curve space demand. Then through a column generation procedure, we're going to identify a highly priced or highly valuable candidates of the development decisions. Then when we have all of them identified, we're going to solve a recourse problem where we can quickly evaluate how good those highly priced variables are and denote the best solution across those highly identified decision paths. Then we're going to iterate this procedure for a number of times, and we're going to aiming to find the best development planning abiding by the uncertainty set that we have. Now I'm going to introduce some set of experiments to validate the efficiency of the algorithm and some practicability of our model. This experiment accommodates three different curve space modalities, namely the EV charging stations, micromobility docks, and transit stations that requires permanent infrastructure developments. Also, I have one additional curve space modality named flex zone, which is allowed for a dynamic location and dynamic operation of the space to accommodate different modalities in a customized fashion. Now, first, let's talk about the methodological side and talk about the column generation efficiency. In this figure, the horizontal axis shows the scale of the problem, and the vertical axis shows the profit or the solution quality obtained from the different algorithms. The gray indicated is a benchmark method where we just solved the stochastic optimization model with a state-of-the-art benchmark solver. The blue ones are the column generation based algorithms, and we can compare the solution quality against the benchmark method. We can see for one of the column generation methods, there's practically no difference in solution quality. Whereas one denoted in sky blue, we have a small compromise in the profit or solution quality. However, when we compare the solution time, the trend is a little different. Here, the vertical axis shows the solution time for a single instance to solve each of the model using different algorithms. You can see the rate of increase in solution time increases most quickly with the benchmark method compared to the two column generation methods. To summarize, when we compare the relative difference of different modeling attributes or the performance attributes, you can see regarding profit or solution quality, there is negligible decrease or even no decrease in profit obtained from the two column generation methods compared to the benchmark method. However, regarding runtime, we can see there's a significant decrease in runtime, which means we can run more iterations of the algorithm, which increases the chance or probability of denoting a better quality solution using the column generation methods against the benchmark method. On the practical side, I also want to show how this planning can show the benefit of different budgeting strategies. First, I want to evaluate the expected profit and the long-term profit obtained from the stochastic optimization model. On this heat map, the horizontal axis shows the total budget allotted for the improvement for the entire time horizon. And the vertical axis shows how much budget can be used for each time frame. So the vertical axis can be translated into how flexible are we in using the in the improvement budgeting. We can have two observations from this heat map. First is somewhat an intuitive observation where the marginal profit diminishes as the budget increases. That is because we consider a finite number of spaces. So at the point where all spaces have the optimal development decisions, having more budget, adding more budget would not necessarily help the system. A more interesting observation comes from the second point where we compare particularly these two cells. This cell on the bottom shows when we have a 3 million total budget, with a 1 million can be used for each time frame. Whereas this cell, we have a $0.5 million lower budget, but we have a greater flexibility of allocating that total budget in a different time frame. We can see that the flexible budgeting will facilitate the higher profit generation even with a lower total budget. This is of great importance because it is considered for inflation, for example, where we can strategically allocate more budgeting in a specific time frame where we can compete the increase of demand or composition levels at different timing. Next is about how we're using the total budget allowance. These results are quite similar to the previous observation. So first, we can see from instances where the total budget is equal to or greater to $3 million, the optimal development flow will not change. And that is because of the same reason where we have a limited number of or finite number of spaces. So if we have all the spaces developed optimally, using additional budget would not make sense. Also, parallel to the previous observation, we can see the flexibility in budget allocation can allow achieving higher profit while spending less in total budget. If you go back to the previous figure, between these two cells, we can have the upper one, which has a $0.5 million greater flexibility, generates about $0.5 million greater profit. However, we can see between those two cases, the upper case is using about $0.07 million lower budget than the bottom case, which means with the greater flexibility, we can concentrate more budget usages at a specific time, which will allow us to have a more strategic and more optimal development planning. So let's summarize today's talk. I have proposed a two-stage stochastic optimization model that helps us to design a strategic and smart curve-space development planning under the uncertainty in demand, volume, and diversity. I propose a scalable solution methodology through a series of methods, including a scenario generation through sample average approximation and the scalability enhancement through path-based reformulation and column generation. With this methodology, I conduct a series of experiments, and I suggest that demand uncertainty can be effectively tackled through a stochastic optimization tool, and budget flexibility allows a more resilient planning that is more optimal in our societal benefit. This is the end of my talk. I'll now open the floor for questions. Thank you very much for listening.
Thank you so much, Jason. Yeah, let's see if we get any questions here. You could type it in the chat box, or you could just raise your hand and unmute to talk. Okay, looks like there is no question. We are ahead of time. That's great. So if you have any questions, please feel free to send it to Jisun. And thanks so much, Jisun.
Thank you very
We're
much.
going to move on to the next one. Sure. Okay. So our next presenter is Dr. Maximiliano Lizana. The title of the paper is Modeling Trip Scheduling Amid Disruptive Events Using Smart Card Data. Max is a lecturer in the Department of Civil Engineering at the Universidad de la Frontera, located in southern Chile, and recently received his PhD in transportation from the University of Leeds. His research is focused on the analysis of public transport systems and travel behavior. With that, thank you, Max. You could start your presentation.
Hi, Sahar. Can you hear me?
Yes, we can hear.
That's fantastic. That's fantastic. Thank you very much. Hi, everyone. My name is Maximiliano Lizana, and the presentation that I'm going to share with you today has the title Modeling Trip Scheduling Decisions Amid Disruptive Event of Bus Commuters Using Smart Card Data. So the main motivation of this work is related to understand the change in public transport demand caused by alteration in situational context caused by external disruption. So in the general concept, disruption can be a very broad number of names of events. For example, it can be the pandemic in a bigger scale, can be a disruptive event, and also can be quite short in the temporal dimension. For example, a metro disruption that could last from a couple of minutes to days, for example. So in this case, we're going to consider more a big scaled event. So the idea here is to understand how this alteration affects specifically the trade-off between relevant attribute in the trip scheduling decision of bus commuters. So far, the literature has made a lot of emphasis in the impact of this event in the side of the trip reduction perspective, and also in the shift from public transport to another modes. But unfortunately, there is a lack of empirical evidence of the impact of this kind of events in the trade-off of the relevant attribute, for example, travel time or schedule delay, a concept that I'm going to explain later, related to the strict scheduling decision. Moreover, so far there is no attempt to employ smart card data in modeling this kind of phenomenon. And most of the current literature is use particularly a traditional survey, for example. So there is a current challenge to employ passive data due to missing variables that are needed for the estimation of these models. So we proposed an hypothesis that was that distinctive situational contexts related to disruptive events have associated different evaluation of the relevant attribute of trip scheduling decisions. So the case study that we considered for our study was the public transport system of Santiago, Chile's capital. Santiago has a population of 7 million inhabitants, and weekly the system record around 25 million public transport trips. So it's quite a big public transport system in terms of demand. And also Santiago is considered the industrial and financial center of Chile. So it's quite a dynamic city. In terms of the public transport characteristic, Santiago currently has around 7,000 buses in the system and a metro network of around 100 kilometers metro line, so that's considered a robust public transport system. And additionally, there is an electronic payment system based on the use of of a smart card called BIP that enabled the registration of every transactions, and what is recorded is the ID of the car, the timestamp, the mode, and the rolling stop. So we use that data for our analysis. And additionally to that, each bus has a GPS gadget that record the position of the bus every 30 seconds. So also we can estimate travel time for every bus in a particular day, for example. So we focus on two particular critical episodes that happened in the city in the last 5 years. One is a social unrest that occurred at the end of October 2019. This social unrest was caused by some social inequalities in Chile. So people go to the street and demand for societal change. But unfortunately, in parallel to this demanding, a lot of looting and violence acts occurred in the city. So many buses were burned and metro stations were also destroyed. So this particular effect lasts many months after the system was completely recovered for these events. And the second consideration, the second event that we analyzed was the aftermath of a long-term lockdown that was imposed in Chile in the context of the COVID-19 pandemic. So we analyzed particularly how trip scheduling decision was in the period called new normality, where it supposed was a freedom, but it was a control freedom after the lockdown, where still many counterfactual measures were imposed, for example, the use of face masks, social distance, and other characteristics. So in this picture, you can see the ridership, the bus ridership from 2019 to 2022. That was the period of analysis that we used. So we located the episode 2, 1 week of smart card data, as the aftermath of the social unrest. That is the first gray line. We don't use the immediate day after this event because the city was completely stopped. So we use it like a stable week after this event. Similar, excuse me, the episode 3 characterized this new normality after the lockdown. You see, of course, that the ridership here was like less than a half than the pre-social unrest. That was the one that was completely reduced, we can say, after, for example, or during the lockdown, that from near 17 million dropped to around 2 million in that period. Episode 1 and episode 4 was also considered as a control ones because episode 1 was considered as a baseline, a pre-disruptive as a pre-disruption characterization of trip scheduling decisions, and episode 4 was like a period a little bit far away of the lockdown, but still can consider some effect from the pandemic in this particular one. So at this point, you can maybe you're asking how trip scheduling decision can be modeled. So well, this can be done through a type of model, a discrete choice model called departure time choice model. So these models are based on a variable that is particular to this model that is called a schedule delay. And the schedule delay is defined as the amount of time of the difference between a preferred arrival time of one particular traveler and the actual arrival time. So for example, if we have a preferred arrival time for me at 9 a.m. in the morning, if I arrive 1 hour earlier, I have 1 hour of earliness schedule delay. And if I arrive 1 hour later, I have the amount of 1 hour late or schedule delay lateness compared to the preferred arrival time. So if I arrive earlier or late compared with my preferred arrival time, I experience some disutility, right? And that disutility could be associated if I arrive earlier, for example, that to a wasting of time, and if I arrive late, for example, to a discount in my salary or some penalty in my work, or if I am a student, also some penalty related to that. So people try to minimize the schedule delay and arrive very close to their preferred arrival time. Okay, so Small in 1982 specify the first the part-of-time choice model where the utility associated to travel at a time interval S can be specified depending on the travel time and the schedule delay earliness or lateness. Both are mutually exclusive. You can arrive earlier and late at the same time, right? Here it's important that this is located in the random utility theory, where it's supposed, or the hypothesis is that people try to maximize their utility. So at the end, people will travel at the time interval, for example, in the morning, that maximize their utility in terms of the variation of the different values of travel time and schedule delay. So the problem with this specification is that to estimate the schedule delay, we need the preferred arrival time. And we don't have the preferred arrival time for passive data. We don't have that luxury that someone that conduct a survey can have. So we need to find a method to impute the preferred arrival time that is unknown for passive data. So the other concept that is important, this trade-off, is in the trade-off between travel time and schedule delay is called travel time valuation of schedule delay. So this is estimated as the ratio between the betas, the marginal utilities of schedule delay and travel time. And that can be interpreted as the amount of additional travel time a traveler is willing to accept to reduce one-time unit of schedule delay. For example, in the morning, if someone wants to arrive very close to the preferred arrival time to minimize a schedule delay, that person probably will travel at the same time of everyone. So the travel time will be quite high, but the schedule delay will be quite low. Other people try to avoid that extensive travel time experience, and they decided to try quite earlier. So they go earlier to the bus stop. There is no one there. There is a few low traffic. There is low traffic on the street, so bus can run through the city, so travel time is low, but they are going to arrive quite earlier. So the schedule delay earliness will be high. So travel time is low, but schedule delay is high for that characteristic. So at the end is the trade-off between both. So the way that we solve the situation of the missing preferred arrival time to estimate this kind of models is to assume the preferred arrival time is a random variable that account for the heterogeneity of the trip time preference among commuters. So in the model, we specify this as a distribution, as a density distribution, which parameters need to be estimated within the model. So we estimate simultaneously the model and the parameters from this density function. And this can be done using a mixed logic model. So in this way, we estimate this path. So at the end, we can get the distribution, a density function for every episode of the preferred arrival time for bus users. We estimate these models only for trips between for morning trips. So we shows an interval between 6 a.m. and 11 a.m. where more of the trips are considered mandatory for for the perspective of the intention of traveling, or another way, they were commuters. So the model for the baseline episode, that was episode 1, the baseline, no disruption, generate expected time in terms of travel time and the value of schedule delay. So both negatives, that's the most important and statistically significant. And additionally, the travel time, the travel time valuation of the schedule delay. That means how much the person is willing to increase their travel time to reduce the schedule delay, was in agreement with other literature where survey data was used. Sorry. And in addition, the path parameters, the parameter from the density function of the preferred arrival time were able to be calculated, and the density function can be drawn from the result. This is the the path density function estimated for episode 1. So we see here in the x axis is the time in the morning, and in the y is the probability, that the high probability to find the preferred arrival time for a person is around 8:30 a.m. in the morning. So that is a very good result in terms of, this is exactly what we expected in terms of the initial starting office time for workers in Santiago. That is around 8:30 to 9 a.m. Okay, so we also studied some differences in the penalties of travel time and schedule delay for different kind of type of users. We consider recurrent user and occasional users. We found that recurrent users are less sensitive to travel time. That means that they are more used to experience high travel time without feel the same disutility than an occasional user. But on the other hand, they are more sensitive to schedule delay. So recurrent users try usually to arrive to the close to their preferred arrival time with less chances to arrive earlier or late. Okay, so they have a more restricted schedule. And this, as a travel time of as the evaluation of schedule delay is a ratio between these two variables, we found that the recurrent group has a willingness to accept travel time to reduce schedule delay 3 times higher than the occasional group. And this is the difference between the density functions between recurrent commuters, that is the blue one, and the light blue are the occasional commuters. So occasional commuters has a late or a right shifted density function compared with the recurrent commuters. Okay, so these are the results for the 4 episodes. Remember, episode 1 was the baseline, no disruption. Episode 2 was after the social unrest. Episode 3 after lockdown, COVID context, and episode 4 a period a little bit far away from the disruptive episode. So we found here that the valuation of schedule delay was experienced almost no change for the 4 episode in the case of the occasional commuters. So occasional commuters seem not to be the trip scheduling decision of occasional commuters seem not to be affected by the different kind of events. By contrast, in the case of recurrent user, we found that from a travel time from evaluation of schedule delay of 1.66 in the initial episode, that value dropped half for the episode 2, that is the after the social unrest. That means that after the social unrest, people were less willing to experience a high travel time to reduce schedule delay. And that means that the demand for that particular episode should be flatter in terms of in the other one. Means that people are not willing to travel in the period of maximum congestion in the network, but they are traveling to or are more willing because the penalties of a schedule delay are lower compared with the other value. Okay, and the situation is even worse in terms of this valuation for the episode 3, where the lowest travel time valuation of schedule delay was obtained of a value of 0.49. So here people definitely avoid congested time and decided arrive quite earlier compared to the preferred time or quite late compared with the preferred time in order to avoid experience higher time of travel time. One of the
Sorry to interrupt you, Max, but we've reached the end of your time. If
yeah,
could
I
you
can drop.
conclude your presentation shortly, that would be great. Thanks.
Yeah, no, I just I just want to show the last aspect here is like the last aspect that I would like to say here is that even in 2022, a period 1 year and a half after the pandemic, the willingness to increase travel time for reduced schedule delay is still quite low. That means there is long-lasting impact in terms of the penalties to of arriving early or later. In other words, people experience now less restrictions to arrive earlier or later compared with the pre-disruptive events. That was one of the findings that we found here. Yes, that's all. Thank you very much.
Thank you so much, and I apologize again to interrupt you.
No, thank you, Master High, for the interrupt. So sorry for that.
No problem. So let's see if there is any question for Max. Okay, looks like we have no questions. Thank you so much, Max. And we're going to move on to our next presenter, Lily Zhang. Lily is going to present their paper on quantitative analysis of urban flood effects on human mobility and point of interest visits in Lagos with integrated spatiotemporal data. So Lily is a PhD student at Villanova University with a background in environmental science and transportation systems. Her research explores the impacts of extreme weather on human mobility and public transit resilience. With that, Lily, the floor is yours. Go ahead with your presentation.
Okay, thank you for kind introduce and good afternoon, everyone. I'm Lily Zhang and from Villanova University, and today my present is about county analysis of urban flood effect on mobility and points of interest to visit in Lagos, Nigeria, and is including this 4 part. First, I will talk about like urban flooding affects nearly 1.8 billion people globally, and Lagos represent a critical case, ranking among the top 50 cities for sea level rise exposed and projected to worsen significantly by 2070. And beyond the physical damage, floods distribute the entire urban system, like mobility networks, service accessibility, and economic productivity. Well, the research gap is substantial. While physical flood impacts are well documented, behavior responses remain poorly understood, particularly in low and middle income countries where data infrastructure is limited and this constrain both immediate disaster responses and evidence-based resilience planning. And especially for causal inference in flood research faces persistent challenges. Unlike discrete shock with defined temporal boundaries, urban flooding unfold gradually with overlapping episodes and ambiguous onset periods. And the fundamental identification problem is in citywide disasters, where do you find unaffected control groups? Traditional approaches rely on geographic controls or simple before-after compare that cannot account for confounding factors, seasonal variations, concrete policy interventions, and economic trends. Additionally, low and middle income lack the data infrastructure for traditional impact assessment. Infrequent mobility service, underdeveloped monetary system, and limited real-time facility access data. These constraints have hindered rigorous causal analysis in the context where the flood variable is highest. So we address these challenges through four methodological innovation. The first is integrate difference in differences with synthetic control method for enhanced counterfactor construction. And the second is developed empirical diagnosis for control group selection when geographic control are unavailable. The third is demonstrate multi-source data integration with find causal framework. The fourth is ensure transferability to data scale in low and middle income countries environment. Our application leverage Lagos, Nigeria from June to July 2020 flood season as a natural experiment with rich multimodal data availability. And our framework involves three integrated steps. The first is flood exposed characterization using satellite image and high-frequency precipitation data for precise temporal destination. And the second is spatial unit definition through OpenStreetMap points of interest into urban sector and the mobility environment, while local-based survey trip records providing daily sector visitation patterns. And the third is causal impact estimation using enhanced difference in differences with diagnostic validation. Well, we integrate four data sources for the flood characterization. The first is Sentinel-1 SAR provide nearly 6-day flood extent mapping at 10-meter resolution, enable objective inundation detection. And the ERA file precipitation data offers daily rainfall measurement and base correct for temporal accuracy. This environmental data validated through satellite precipitation convergence, and the local-based service data compares nearly 4.6 million geoforce trips spatial mapped to points of interest category, generating daily sector visitation time servers from June to July. And temporal segmentation defines four analytical phases, including benchmark, preparation, flood, and recovery period. This structure enables phase-specific impact estimation across the complete disaster life cycle. We also address the fundamental control group identification problems through empirical detector rather than geographic assumptions. Two metrics guide selection. The first is maximal information coefficient, which measures the precipitation vegetation dependence, and the coefficient of variation, accessing temporal stability across flood phases. Well, MIC identify POI category with minimal weather sensitive and severe average consistency of vegetation patterns, isolating thematic flood-related variation from random fluctuations. Lower value on both metrics indicate super control candidates, and this data-driven approach provides objective reproducible control selection application across disaster contexts. And we also employ analytical approaches for robust causal identification, including standard difference in differences, compares temporal evolution of treatment versus control groups, with integration terms capturing causal effect. And also enhance this through synthetic control method, constructing individual counterfactor for each treatment sectors. rather than assume uniform trajectories. This synthetic control DID uses ridge regression with non-negative construction to optimal weight donor units and matching sector-specific pre-treatment dynamics. This parallel trend assume patient inherit in standard DID accommodating heterogeneous treatment effect characters of complex urban system. And each sector receives customer synthetic baseline, improve causal identification in dynamic environmentals. Multi-source validation provide rigorous flood event characterizations. Precipitation analysis shown in June to July 2020 and capture 8.5 times baseline rainfall during flood period. And satellite image confirms progressive induction from June 23rd, July 5th, temporal aligned with precipitation peaks. And the spatial analysis reveals flood concentration in West Logan and the least region with highest population density and mobility data coverage. Convert validation across independent sources confirmation temporal boundaries capture flood life cycle rather than attribute prediction and providing objective fundamental for causal analysis. Diagnostic screen yield clear empirical result, like the red figure is the MIC result and the CV result. Religions POI demonstrate the lowest precipitation sensitive, like MIC equals 0.194, while transportation shows highest dependence, like MIC equals 0.47. And the residential POI shows supertemporal stability. Its CV is just 0.012 compared to more validated sectors. Result along with theoretical expectations. Religious attendance maintain consistency regardless of weather condition, while transportation systems show upwards weather variability. Residential across demonstrate expectational stability across all analytical periods. And this validates selection emulated attribute control group assumption common in disaster research, providing objective fundamental for subsequent causal inference. And this approach offers transferable method for control identification in other urban disasters. And here is the cross method validation demonstrate robust findings. Like healthcare shows consist positive effect across all specifications, nearly 40% increase in visitation during flooding, and statistically significant in every approach. And this reflects emergency medical demand from flood injuries, waterborne disease, and all mental health crises. Transportation shows opposite patterns with consist nearly 20% decline across method, reflecting infrastructure damage or behavior avoidance. Effect remains stability significant across specifications. Synthetic control provides enhanced process through narrow confidence intervals, demonstrating methodological advantage. Optimal weight of control groups enables detection of the moderate effect potentially missed by single control approaches. Cross-method consistency validates causal interpretation of observed effect. A full disaster cycle analysis, including pre-flood, flood period, and post-flood period analysis reveals temporal heterogeneity in sectors' responses. For example, preparation phases show minimal anticipatory adjustment across most sectors, rather than flood and post-flood period. With education, category shows modest decline reflecting institutional partners' protocol, and the recovery phase demonstrate most significant findings, like healthcare demand 50% above baseline, and the impact component over time rather than reservoir. And the accommodation surges 40 to 60%, reflecting displacement driving demand for temporary housing. Retail shows strong recovery at nearly 20 to 30% through pent-up demand mechanics, and the transportation demonstrates no significant recovery, and indicating persistent infrastructure constraints. And these patterns reveal recovery as distinct phase with unique dynamic rather than simple baseline reversion, requiring phase-specific policy intervention. Two primary contributions shows the first is we provide rigorous quantification of urban flood impact in Western Africa. Lagos, Nigeria shows the healthcare burden intensification from 40 to 50% flood to recovery, and the persistent transportation constraints at 20% decline with no recovery. Second, we resolve master challenges enable causal inference in citywide disasters through objective control, selection, and kinetic counterfactor construction. And our framework demonstrates transferability to data scale in low and middle income area using commonly available data sets like satellite image, mobile data, and the perception records. Thank you for listening, and questions are welcome.
Thank you so much, Lele. Is there any question for Lele? Okay, looks like there's no question here. Thank you so much, Lele.
Thank you.
Sure. And we are gonna move on to our last presentation titled Analysis of Public Sentiment on Parent-Taught Driver Education Using Online Comments. This presenter, I contacted the presenter, but I didn't get a reply back, so I'm hoping, are any of the authors here?
Yes, I'm right here.
That's good. Okay, that's great. So, Faraji, yeah? So Faraji is a PhD student at Cleveland State University. If you could just give us a brief bio of yourself also, that would be great. And yeah, please get started with your presentation.
Okay, thank you very much. My name is Faraj Rajab, and I'm a PhD student at Cleveland State University. And in my research area, I'm mainly doing text analysis by using the online comment and the cache citation from the DOTs. That is my area of research up to now. And up to now, I have completed my first semester at Cleveland State University. And thanks so much. And in my presentation today, I want to present an under-research, and I can say it's like an odd topic, which is called the parent-taught driver education. And my paper goes by the name of the analysis of public sentiment and the perception of the parent-taught driver education by using online comments. I'm pretty sure you can see the slides, right?
Yes, yes.
Okay.
We just
so-
see the first slide, so if you no, we just see the first slide. I think, are you on a slide? What
Yes,
slide
of
number
course.
are you on currently?
I'm giving the brief introduction first.
So it's
Okay,
the
so let's moving forward in my presentation. So in our first slide here, I have the list of my co-author, which is Abdul Ngereza, Philip Baragat, and Karen Bikuba, who are also the graduate research assistant at CSU, and our principal investigator, who is Dr. Emmanuel Kidando, who is now an associate professor. And this is our outline in our study, and I would like to go straight to our introduction on motivation for
would
this
you
course.
would you mind sharing it as your make it bigger, the slideshow? Use the button down there.
Yeah.
Yeah, there you go. Okay.
Okay, good. So starting with a brief introduction, we all know that we have a problem of teen crashes, and the statistics from NHTSI show that young drivers, they are highly involved into the road crashes. And one of the key strategic methods which was introduced to reduce the number of teen crashes was the train driver education, which was introduced to ensure the teen safety and the mobility. But the existing driver, the existing driver education that has been offered to schools over time has a couple of limitations, and one of this limitation I can say, like, they include, like, due to high cost for families, especially from middle and low income uh, zones, and also to some places, especially in the rural, this driver education program, they are limited in terms of availability. And also the key limitation of the traditional driver education programs is the insufficient behind the wheel practice hours for these teams. So due to this due to this due to this limitation, and it goes out to a growing alternative, which is para which is para which is para which is parallel taught driver education, and simply we can say it is PTDE. And up to now, it is a growing form of driver education in the United States. More than 4 states have adopted it. Like here, we have Iowa, we have Missouri, Oklahoma, and Texas. And so, coming to our research gap, we are trying to, due to the growing presence of the PTDE, which is the parent taught driver the the parent taught driver education, there is still a lack of understanding into the public perception and the experience about these programs. And this is our key focus in our study. So before diving deeper, let me walk you through the driver education background in the United States. And we can see that the evolution here in the driver education in the United States has been shaped by factors like the increase in the vehicle ownership over time, also the road accident, and also the societal needs. And starting in the early years, which is 1930s, at first we had the informal driver, we had informal driver, we had the informal driver, we had the informal driver, we had the informal driver education, and it was mainly provided by the family members and the car. It was mainly provided by the family members at that time, and at this time, as I have mentioned, it was informal. So it was informal driver education program. That means there were no the classroom teaching and the behind the wheel practice, and everything was done informal. And then we come to the period which is 1930s to 1970. As I mentioned earlier, due to increase the car ownership and the road accidents, the driver education was introduced in the public school in the United States. And at this time, it was a time that the formal driver education started in the United States, that combined the classroom hours and behind the wheel practice. And we came to the shifting we came to the shifting landscape from 1980s to 2000 to early 2000. And here, the driver education that was introduced in the public school was redirected into the private sector due to the cost of budgets in the government public school. And also, we came to the period here, which started from 2000 up to the present, which is the program that is denoted as the GNL, the Graduated Drivers Licenses. And this is the modern form of driver education program, which is characterized on passing these teen drivers into 3 stages in order to certify their driving licenses. And in this program here, which is GDL, it is also characterized by the involvement of the parents in order to ensure that the program is effective, especially for the section of the behind the wheel practices. And so our key discussion here is to introduce the concept of the parent-taught driver education, which is simply, it started a long time which is simply started a long time, but up to now there are still like the workers into the research. But as I presented in the previous stats, some of the states they have started to implement it, because if the parent is the key input into the driver education, so there is a possibility that a parent can be empowered to take control over the whole process of driver education to their kids. So coming to the section of the objectives, as I presented, we are trying to investigate the public sentiment and the perception regarding the PTDE program by analyzing the online comment, and basically we quantify the sentiment and also to identify the key discussions which are presented in this comment. And our approach, we are leveraging online the discussion, and our data we extracted from two online sources, which is Reddit and the parenthood.com. And we employed an advanced computational text method, which in the basis we employed the sentiment analysis, and also we performed the top key modeling by using the LDA and as well as text network to provide the visualization of this co-occurrence words which are appearing in our discussion from these two sources. And what we are targeting in terms of contribution and the policy relevance, we are focusing to provide the data-driven insight into the public acceptance and the specific concern about this program, which is PTDE. And also for the later on, we also want to inform decision-making agents like state DOT, and also we can say DMV into actionable intelligence policy, and also the program involvement. And also this can align the PTDE program with also the public need and also the perceived effectiveness. And so our data sources is Reddit, and we extracted data which ranged from 2015 to 2024. It has a broad discussion into this driver education program, and also we have we had the data from the website that is called the parenthood.com from Texas, and the data ranged from 2021 and 2025, and they are basically the feedback on the PTDE causes in this region, Texas. And as you can see here from the range of data which we have, this is the available data set that we tried to collect based on its availability. And the method which we used to extract these data, we did the web scraping. And in terms of legal issues, these two sources, they are open sources. And for the statistics, we had total comments of about 2,800 plus, which of which 300 came from the Reddit and 2,500 plus came from the parenthood.com. We perform the text processing techniques for our models. So let's move forward to the section of methodology. And in our analysis, starting with the data collection and the pre-processing, we employed these three analytical techniques. The first one was segment-based method by using radar, and this is quite a good text mining technique for social media text. And for what we were trying to record from this text, we also established the sentiment score as positive, neutral, or negative, and also we performed the top key modeling by using the LDA in order to identify the underlying theme into this discussion from both two data sources. And also we developed the text network in order to give the visualization of co-occurrence words in order to complement the results of the sentiment analysis which we performed. And the tools which we use the natural language toolkit, and also we use the library which is Jensen and R for developing the text network. And this here, it shows our methodological overflow from the data collection up to the output, and our output is divided into three parts. The part of the sentiment, we have the sentiment score from both two sides, and also from the LDA modeling, we also tried to we also revealed the latent topic into this discussion, and from the text network, we also provided the visual which show the word and their co-occurrence into this analysis. So starting with the sentiment analysis results, the overall finding, it showed that from the parent.com website, we have the positive sentiment, which is predominant, about 83.6, and also the negative 14.8, and the neutral one was 1.7. And this shows that the PTDE, according to the parent driver education website from Texas, it is highly acceptable and favored. And also coming to the Reddit shows the 51.6% as positive sentiment, 24 and 24.6 as negative and neutral respectively. And coming to the topic modeling for the parent.com, we can see here from the LDA diagram, the left side shows the intertopic maps, and we created over 15 topics, and also the right hand side, it shows the most 20 salient words in each topic which we selected here. And in our discussion, we selected topic number 7. It is because it is more relevant to our discussion. The words here, they support the result which we got from the sentiment analysis. And we can see here from the chart, the word which are more predominant, we can see words like easy, think, texty, and pretty. And all of this, they give us the insight that this program is perceived as positive, which is easy and efficient. And how we come up with a topic from this analysis, we use the silent words. And also
I'm sorry to interrupt. I'm so sorry, but
okay.
we've reached to the end of your time. If you could please
Okay.
conclude your presentation, I'd appreciate that. Okay,
good, no problem. Coming to the Reddit, and also we have the silent words here, and the key dominant theme here is they show the parental involvement, the driving school, and the practical experience as the topic from the silent word, which I mentioned here, like drive school, take parent, and drives. So moving to the test network. And also we can see here we have the network of co-occurrence word. And in the middle here, we have word like easy greets, which also this result they're trying to complement what we found in the sentiment analysis. And also moving to the Reddit, the discussion in the Reddit, they were very broad. The co-occurrence word, the show first driving test the pass, which also highlighted that the success in passing the driver education test. And also we have the terms like car, parking lot, hour, which indicate also the importance of practice and the commitment in the driver education. So these are the key findings, which is the positive sentiment, and also the platform showed the higher favorability due to its user context, and also the key themes which we extracted from the top modeling involve the value of parental involvement, and also it showed that the PTDE program, it is more accessibility and also a user-friendly program. And the crucial role of practical driving experience and effective parental guidance. Moving to the implication and the recommendation, our target is for the police it was for the police makers and the transportation agency, as we want them to acknowledge and leverage the high public acceptance for the PTDE. And the actionable policy recommendation first is to adapt this program, which is PTDE, for other states which they haven't yet introduced this program into their states, and the more actionable would be like for states which they have implemented this PTDE. We suggested that they could also have the targeted intervention, like to implementing method like the checklist in order to ensure that this program is effectively handled in their state. And also
thank you,
some
Faraji.
discussion.
Unfortunately, we are out of time, so I'm gonna stop you there. Thank you so much. Is there any questions for Faraji? Okay, if not, thank you all for joining us today and for your participation, and a special thanks to our presenters for sharing their work. That concludes our session. Enjoy the rest of the conference, and thank you, everyone. Have a great day. Bye.
Thank you very much.
Thank you, presenters, and thank you for sharing.
Sure.